whatever. Seems like the mouse is not working very well today. But anyway, whatever. So one question, would be next Thursday. Officially there's no class, right? Because due to 那个 reason that is graduation ceremony, but I guess you guys should be okay to have class, or you want to do it makeup. So that is the case like this. Let me show you. Because according to I don't know whether you read Chinese, but let's do English. It's configuration. So and daytime class postgraduate programs are suspended. So I have to see if we need to either two ways to do it. Either we have to do the makeup, or the classroom is here, is there, no problem. So the question is whether we schedule makeup or we just go ahead. Just vote, maybe easier. I just end this guy. Maybe I ask maybe ask first, right? Maybe I ask first. Then multiple choice, just two, I guess. The makeup day probably would be maybe following the standard makeup is like December 1st and 2nd. Unless you have some special reason. That if the makeup, then we decide makeup day. But let's see whether we continue November 6th or we do otherwise. Okay, let's see. Okay, you can tell me we can make it. Don't waste time, just make it 1 minute to vote. With A and B, right? Just tell me whether you want me to do makeup or maybe 1 more minute, I guess. Guess seems that's not sufficient. Because I noticed that we have to solve this problem first, otherwise the tutorial have to reschedule, right? Because otherwise. Okay, so according to the rule, I mean, anomalous rule, so we just have class as usual next Thursday. The room is booked, so that's why we don't need to work out things, and I don't think anyone going to further with me, I guess, shouldn't be affecting. Anyway, the class is record anyway, so in case you really want to attend to take some pictures, feel free to do it. So that's why the tutorial will go ahead next Thursday as usual. The deadline is also next Tuesday, so make sure that you have time to work on your homework 3. I think just 2 questions. If you're aware, it's simply 1 question uncertainty and 1 question for static games. Okay, so shouldn't be spending more than 2 hours for the whole assignment, including your time for revision. Okay, so shouldn't be spending too much time on that. So let us continue our class. I guess it's a good once we settle down with the thing. So I just very briefly went over this again quickly. So because we're talking about dynamic games. So so as you see, we have done the first one. We've put the second one, dynamic games of company information. And as you recall, the static game of company information have the ideal Nash equilibrium and dominant solvable. And that is, we know, a good solution when we're talking about static game. Static game doesn't mean only in a static world. It simply means that when one of the player make the decision, the other guy is not aware of the result. Okay, doesn't have to make the same time. So you can imagine the standard case of a still big auction, right? Everyone write down the price he want to bid for an item and put an envelope and put in the box. And once it's over, everyone open the box. Now this is also a static game. Okay, but of course, it's whether complementation are easy, but it's a static game in the sense that you don't know what other have chosen. Okay? So for dynamic games of company information, and then we mentioned last time, right? And Nash equilibrium will be a poor predictor of the outcome of the game, right? Remember matching pennies, right? So in the dollar, matching coins, where player 1 would win if the coins are were defined the same. The coins are different, and player 2 want the coin to be same size, same faces, and we know that player 2, who is the second mover, for sure would win because he knows which side to show, right? Player 1 would always lose, and clearly it has a pure strategy, we'll call equilibrium, right? But the Nash equilibrium will be the mixed strategy, right? And mixed strategy doesn't make sense here. I mean, no matter what player 1 randomized, the player 2 would have a strictly dominant strategy. So the Nash equilibrium doesn't work here. And how can we make it work, right? And we use the idea we call parallel induction, right? Which is looking at the game at the end, okay? And look at this subgame, we solve it, right? Backward, right? Because everyone take turn to make decision, and each one will optimize when it's time to make decision, right? And Shelton actually won the Nobel Prize for making this barrel induction formalized as a subgame perfect equilibrium, which require Nash equilibrium in every subgame. Okay, that's basically combined barrel induction from dynamic programming to Nash idea inside the game. So basically, the combination of two lead to this one. Okay, I hope you recall this example. We have would be player one would have two strategy A and B, but player two would have six strategy, right? Because player two were three at the left look and the two and the right look. 2 times 3 will be 6, right? So that would be the idea, and there will be 3 subgame perfect Nash equilibrium. And of course, while we say subgame perfect equilibrium is good, it does require players are very sophisticated. So this example of this center game in experiment turned out to be doesn't fit our subgame perfect prediction. In this game, the subgame perfect prediction would be immediately player one would choose S. Okay, and very rarely in experiment you will see stop at the beginning. You will see C continue at least for 3 to 4 rounds before actually stop, right? Because every round actually 3 to 4, I mean, suppose you end up in either this or this is Pareto dominate this guy, right? So basically it's not something that, I mean, people will have some kind of trust, but not so much trust. That would be something you expect things to happen, right? It's like, I think people in China, I mean, we learn Chinese philosophy in the, we learn from Confucius, it's like, Mengzi, right? We learn human are good, right? And Mozi said, I think human are bad, right? I think we are somewhere in the middle, right? We are not really selfish, but able to collaborate somehow. I think evolution actually have some DNA in a gene that we kind of collaborate in some sense, but we are some selfish in some aspect. So that means that we are not fully selfish, or we're able to see somehow, I mean, something would happen. But anyway, that is what you expect to be. So that's why, and also we are cannot see that far, right? Maybe we are machine that we're able to see. Actually, everyone will choose S here, but I think it's like not everyone are that sophisticated. I mean, think ahead of 6 steps is very difficult. I mean, you ask professional chess player, probably they can only think ahead 3 to 4 steps ahead. And if you require player to think 10 steps ahead when you do barrel induction, probably it's not that realistic. Okay? And that's why these days you look at papers in top journals in business, right? They need not use a subgame perfect equilibrium or even Nash equilibrium. They will relax a little bit, just allow some kind of deviation, not all type of deviation. And the reason is it requires too strong, the solution cost is too strong to be meaningful for this one, right? It's like this is too strong. You can imagine if they can only think 3 steps or 4 steps ahead, then you get end up in something in the middle. Okay, so it's like bounded rationality. So that's why in the recent 30 years, and there's a lot of papers, theory or experiment on bounded rationality. It's like people cannot think too much, right? And of course, some other people in the early days will talk about information constraint, right? It's like they don't know the game down deep enough, so that's why they do that. Or now this day they don't do the shortcut, rather they will think people cannot think that far away, right? So that would be something that it will be taken into account. So here we have extensive fun game with simultaneous move, right? Just if you recall, we stopped last time is we will denote in the information set, right? In this case, player 2 can't distinguish he's in the left or the right note. That means that his strategy is not 4, only have 2 strategy, because he can't tell player 1 has chosen head or tail. And this game tree is indeed the standard matching pennies game. And you would expect only mixed strategy, right? Because player 2 doesn't know what player 1 has chosen, so he would randomize, so that player 1 would also randomize. So that would be the main idea behind, because if player 2 have fixed strategy, either head or tail, player 1 will exploit, right? If player 2 for sure choose head, player 1 would choose tail, and vice versa, right? Because player 1 want to be different. So that means that player 2 have to randomize over the 2, and if player 2 randomize, player 1 will also randomize. Now, I think we stopped here last time and asked you to try what are the strategy. So I hope you did try, okay? But let's tell you the answer. So player 1 strategy set is in the first note, he has 3 choices, A, B, and C. So he has to choose A, B, and C, right? But he also is going to move here, okay? And he doesn't know where he is, so his only choice F or G. So the strategy set will be 3 times 2, A, B, C times F or G. So that would be 6 total, in total number of strategy for player 1. And for player 2, it will be D or E times H, I, J, again 6. Okay. And probably there's nothing new here, but the more tricky part is player 1, even he has choose B, he has to say F or G. Okay. And you may ask why, right? Because once player 1 choose C, for example, then the game is over, right? So why I have to specify F or G, right? The reason is, remember, we have to check subgame perfect equilibrium. Without saying player 1 what he's going to do, it's impossible to check what is Nash equilibrium in this game, okay? So that's why strategy, you have to specify for all possible strategy, even though the game is not reached there, okay? Even C is being chosen, you still have to specify F or G, okay? Because how to justify choosing C? It must be player 1 don't want to choose A, right? Better A, right? If we don't know what's going on here, how can he make the decision? Okay, so we have to specify this. And this seems simple, but you may often commit a mistake when you write a model, because very often when you write, say this is time, the game of timing, so we often say if player 1 do something, player 2, in the time 1, player time 2, what happened, right? And if third one exit, right? And probably the game is over. You don't want to model it, right? But if the model, if player 1 enter, then the game will continue, right? So without modeling those, it's not complete, right? Even though it may be dominant in your mind, this is going to happen, okay? But it's not strictly dominant until you solve the model, okay? So that's why you have to carefully specify what happened. Okay, you can't skip that. Maybe you can push it to the appendix or footnote, but you have to let people know that you actually thought about those things, right? I mean, you may say, okay, because everything here is strictly dominated by that, I can forget about this. That's fine, right? But you have to let people know that's the case, right? Otherwise, you're not doing the right job. If you want to employ subject perfect equilibrium, right? Because otherwise, it's not right. If okay, if you proper Nash equilibrium, because but otherwise, to be very careful. Okay. And how many subgame? I forgot to mention subgame in this game. This is one subgame. Okay. And this is another subgame. And this is the whole is this subgame. Sorry for the mouse because I don't know, the computer has some problem. The mouse doesn't work very well, but that will be the free subgame here. So that means that you have to solve Nash equilibrium in this free subgame. Okay. Or what we do barrel reduction. I can't erase this. Will make the mouse not working. Okay, thanks. Done. So this is another famous game you can find in my textbook. It's called a niche choice game. So in the first stage, the newcomer decide whether to stay out of the market, which is out, and get in the market. Okay. Once you get in the market, you can decide simultaneously with the incumbent whether they want to focus on the smaller segment of the market or large segment of the market. Okay. If they both go to the small segment, they all lose $6 because the market is small, right? And they focus on large market, they all lose $3 because they also compete there, right? But if the entrant focus large and incumbent small is losing money, right? So the newcomer earn $1 and small lose $1. And vice versa, if the entrant choose small, you get -1. And if you incumbent on large, you get 1. So whoever go to large will get $1, right? And the one goes small will get -1. So the question would be, what's the solution to this game? So as we said, subgame perfect equilibrium would be equivalent to barrel induction. So how can you solve this game? Would be looking at the last subgame, okay? And then look at this game and solve the equilibrium first and replace equilibrium outcome there, okay? And then we solve the game backward. That's called barrel induction. So this game, as you can see, is like the anti-coordination game, right? It's like they don't want to be the same, right? They want to be different, okay? So, and you will easily see that there will not be a pure surgeon Nash equilibrium, but because this is game, it's just a normal form game, right? So they move together, there are only two strategies. So that means that we can solve it by looking at this game tree. There's no different from what we learned in the last topic. So, so there's a pure strategy, sorry. So look at this. Player 1 don't want to go up. That's check. Check player 2. Player 2 doesn't want to go to large? No. Okay. So we confirm this is Nash equilibrium, right? By checking whether any player will want to choose other strategy. Okay. And let's check this as well. Okay. Check now. Player 1 won't deviate. If you deviate to large, he get -3, which is not profitable. So this is no. And check player 2. Will 1 go to -6? Again, no. So that means that this is 2 Nash equilibrium. Okay. And you can easily check the other 2 are not. So you check all of them. Of course, you may also want to check whether there is a mixed strategy, but I guess no, but you can check it out. So now the question would be, we have 2 Nash equilibrium, right? Then how to do backward induction? Then you have to do case by case. You have to do both cases, okay? So we will do backward induction in 2 don't allow me to clean up. Very bad. Okay. So we replace by large and small and large. Okay. And in this case, player 1 compare 0 or 1, right? And that's why in. So there will be a subgame perfect equilibrium where entrant choose in and large. The player 2, the incumbent, choose small, right? So that's a 1 subgame perfect Nash equilibrium. And the other would be player 1 decide whether out or in with small. Okay. But in this case, it will be out because 0 is -1. So it will be out small and large. So probably now we have 2 subgame perfect Nash equilibrium. The question would be, what can we say? Right? We have 2 very different results, right? If you look at observation, you only see in or out, right? Because, and also in, you will see out as outcome or out with large and small, right? So how can you actually say which are prediction? So same as static game of complete formation. This is what subgame perfect brings you. If you will want more, you need further refinement. Okay. It will depends on the strength of entrant, right? You will imagine there's something that beyond the scope of the model. If you imagine that it's entrant that has a stronger financial background, or he's stronger from other industry, or he has deeper pocket, then you expect this will happen. Something left happen on the right side, right? Or the new entrant is a new startup, is weaker, then probably out is the thing you observe. So it really can't say too much based on game theory. You probably need to look at some custom, some focal point, or some other thing to say which would you pick if you have to pick. Okay, and there's always a problem of game theory, right? You have 2 choices and what should be picked, right? And when you do empirical part, how can you do? Okay, you can't really say too much. But at least if this is a game they play, you should see at least the game theory predict 2 things, right? It may stay out, okay, that's fine. But if in the new entrant focus on large segment of market, where the big firm will focus on existing firm, focus on small, okay? So that would be something you predict, right? So that is something we can say, but nevertheless, we can't say too much beyond that. And probably, as we said, right, it's same as the static game of company information. Maybe something you didn't model well, so that's why you leave some uncertainty, right? And there may be some reason why the new entrant may be to be advertising before they go to the market. They will actually signal where they would do, right? They will say, I'm coming for the larger market and make a credible threat. Okay, very credible. And there may be some way burn the money. There are many strategy, right? And indeed, that's why you are here, right? There's a marketing people, your strategy people try to make this game solve, right? Is to do different business strategy. In this way, then you know the answer. Okay. But at the moment, game theory, if you have this model, you can't tell. Okay. If you want more, either you give me more detail, okay, explicitly model it, or you argue it in your application why one equilibrium is better than others. Okay. So that's what I can say. So here we let's talk about this example and with a break. Okay. So this is also a very famous game of competition. It will be Carnot, Bertrand, and Stackhoper. So these three are the basic game probably you learn in undergraduate IO or game theory you learned before, but if not, it's okay. We just learn it. So I hope after this class you know it. And Stackhoper game is like firms can compete in price quantity, but we focus on quantity. So as a Carnot model, so you can see linear demand, inverse demand function is A minus Q. Homogeneous good, so total market is Q1 plus Q2. And cost is constant marginal cost without fixed costs. So profit will be the price minus cost times quantity. So that's very standard model. So here is what is Stackhoper is one of the firm would move first, the other firm would move later after observing the quantity. Okay, so it need not be quantity, it can be price. Okay, it can be Stackhoper price competition and Stackhoper quantity competition, but I think we'll focus on quantity. And this model is often used, and very often the first mover are the market leader. For those who are in accounting, probably you know the big five. There were big five, but now it's big four. But big four can be considered as first mover, right? Because they probably set the price and the other firm will just follow, right? Because they will set what's the price. Or you look at the international oil market, the big player are Middle East country like Saudi Arabia, those countries would set the quantity and price, right? And other non-OPEC player would follow, right? So that would be the case. And you guys are probably too young, but in the 90s and 80s, and we often gas station in Hong Kong or other places in the world, they will announce what's the price through the TV. They say, okay, tomorrow our gas price would be this much. Okay, and basically other firm would follow pretty much. Okay. But anyway, so firm one, the leader, the price, the quantity choice is free to choose, right? But firm two will be more complicated, right? Because he has to make the quantity choice after observing firm one. So firm one is choosing a number. Firm two is choosing a function, because he has to respond for every possible quantity that firm 1 might have chosen. So firm 1 is choosing one thing, one number. Firm 2 is choosing, for every number that firm 1 is giving, I have to provide a number. So that means that firm 2 is choosing a function. It's not a number. So that is very complicated, right? Because if you think about the game tree, it will be quantity for everyone. So basically like this, right? Firm 1, right, will choose many different quantity, right? And firm 2 is moving here. He have to say whatever thing with every note, every subgame, right? That means that firm 2 has to have a quantity, right, to do it, right? Basically, firm 2 have to come up with a playbook, right? And when he see this, firm 1, I do this. And when I switch this, I do this, okay? So firm 2 is a function, have to have a playbook, okay? Have to have a instruction to follow. So that's why I write from Q1 to R star, okay? Real number, R plus, right? So although firm 1 is choosing a function, but it's not something complicated. Basically, we're solving for the best response function. It's something that we know very well. So how to solve this? We employ Babel induction. Okay. You will imagine that solving this would be crazy to solve because there's so many, there are actually infinite many subgames. Okay. How can we solve all these subgames? Okay. But the good thing is we can solve this all subgame at once. Okay. Because we solve a function. So we can consider the subgame where Q1 is chosen. Okay. We keep Q1 as a variable. Okay. That means that when we solve this, we leave it as a variable. So we means once we solve this generic game, we solve all the game because this can be any number, right? So we solve only one generic game. Actually, we solve all subgames. Okay? Actually, it's infinite many of them, right? Just to remind you, this is a very technical step. This is different from, of course, mechanical is very easy, but the idea is much deeper than the math, right? Because you are actually solving infinite many subgames. Because without specifying which Q1 is chosen, okay, it's left it as a variable, which means that we solve for all subgames. Okay. So that means that player 2, firm 2, is maximizing this. This is the price, right? This is the marginal cost. And at this point, I hope it's not difficult to see the optimal is this guy, because the defense with respect to Q2 is contrasting, right? So this is the solution. I think you should be able to solve that easily, right? Because the partial derivative will be A minus Q1 minus 2Q2 minus C equal to 0, right? And you can solve for Q2, which is the answer I have here, right? I hope this is something that is not something too difficult to see. And since this is a construct equation, automatically satisfy second order condition. Okay. So now we actually solve the subgame, right? Because Q2 will be solving like this, right? It's like whatever Q1 they give me, this is his best response, right? So basically this is Q2 best response. And remember, you're solving all possible subgames, right? So Babel doesn't involve this. Basically, you solve this. Okay, and firm 1, okay? Firm 1 knowing firm 2 would follow that procedure. So that means that this Q2 will be expect to be firm 2's best response. right? Because he know firm 2 would choose according to the subgame perfect idea, right? Why this is the case? Because firm 1 know firm 2 is not stupid, right? And if firm 2 is not stupid, he will do the best response, right? So under firm 1 know firm 2 is not stupid, he will maximize based on this, okay? It's maximizing based on the best response function of firm 2, okay? So basically you would plug in this, okay? And you solve this out. Okay. And I hope it's not difficult to see this is true. Okay. And again, because the partial derivative will be a minus 2q1 minus c equal to 0. Okay. Of course, you can over 2, but over 2 doesn't really redundant, right? So you can easily solve a minus c over 2, okay? So this is the firm 1's best response, and you put back to firm 2, okay? And firm 2, this is the best response, and firm 2 will choose a minus c over 4. Okay. So the subgame perfect equilibrium outcome will be this and this. Okay. So do note that the subgame perfect equilibrium is, be careful, subgame perfect equilibrium is this guy and this guy. Okay. Because strategy, right? These player 2 strategies like this. Subgame perfect equilibrium is this and this. But the outcome, subgame equilibrium outcome is this guy and this guy. Let me say it again because it's very important. What is subgame perfect equilibrium? Will be 2 strategy, which is this guy and this guy. Okay. But subgame perfect equilibrium outcome, because that is the outcome, is not a strategy, so we will be a minus c, a minus over 4. Okay. And here, firm 1 is producing more than firm 2, right? Because firm 1 knows that firm 2 would not produce that much, right? Because that would harm them. So firm 1 is having advantage. If you remember, Carnot competition will be a minus c over 3. Sorry. Where's Carnot? It's here. A minus, right? So that means that if firm 1 is first mover, firm 1 actually produce more, and firm 2 produce less. Okay. And in total, they produce 3 over a minus c, right? In this case. Okay. This is what the stack over, and Bertrand will be 3 over 2. Right? Because that will be Bertrand total production. So you can see in the stack over, actually you produce more than standard Carnot. Right? So that means that stack over price are lower than Carnot. Right? Because you have more quantity. So the consumer surplus, of course, is higher in stack over than Carnot. Right? So that would be same. And same as welfare, right? So Stagobird is better in terms of consumer and welfare. Okay. So I think we should break, and so we will be summarizing after break, and then we'll go to what we call with the game, which is by itself can be a whole semester course, but we do it in one class half a class, not one two-third class. But in any case, good. That's a break of 15 minutes, and then I guess we can do the we can do the U reply as standard. And since tomorrow is our Halloween and yesterday is our Chongyan Festival, so I bring you some candy and snacks in case you want. Okay, there's a break. We will come back at 10:40. Case one, celebrate Halloween is tomorrow. There are some break. Halloween. Happy Halloween. Oh yeah. So I have more in office, I think. Yeah. Yes, do celebrate Halloween in China. When I was in Singapore, they say people go around and get candy. Here you don't have this kind of tradition. I recommend you try the once in a while try the Ocean Park Halloween. It's a good one. You go to Halloween, you try haunted houses. It's like $200 per ticket, and go to 300 houses. Last time I bring my kid there, this year it's fun. You go there at night and then like someone try to say, it's really good fun. It's a good experience, right? At least once in a while, it's one of the. If notice, it's like the Ocean Park is almost going to collapse, die, and someone and you was the guy, one who owned the Kai Farm, and he went away to introduce a Halloween there, and it's a good fun. And every is different, so you can go with. I can choose. There are 6 haunted houses. You can choose 2 of them. Okay, you go this or that. You can just try to get this fun. This is not. Yeah, professional type of skating. It's free, yeah. Yeah, if you're lucky, but I don't know that they don't have. I don't they don't hide because on the Halloween paper. Yeah, they send headaches. You're hot in your birthday. But but you can also drive to whatever. Disney is not too childish for our age. But you can still try the Halloween at Disney. It's fun. I mean, but if you don't want to spend any money, it's okay. Tomorrow go to that kind of then also we have a lot of fun. Tomorrow is probably to that kind of there's a lot of people driving up and have fun. There will be and the minimum costless try because you take the East Rail all the way to MOD, right, and then just go out. But one more stop to Central and then go out and then just you can see really just. But of course, you can always have who's really example. And you don't want to go at all. More you guys Halloween style in property. This is the better. This is the Halloween. This is Halloween style. Happy Halloween. Halloween style. That I don't eat fish. Oh. So hopefully you enjoy your Halloween. Yeah. Sorry. Let's continue. So now, although we do a simple example, I think it's enough to illustrate how we solve. Even we give you a very complicated game of complete formation, you simply go to the last subgame and solve backward and solve all the way to the beginning, right? And it seems very simple, but if the game is complicated, then it can be very complex. But given now with AI or all the mathematical or the software, shouldn't be too difficult to solve all the way down, right? And the only difficulties is probably be careful is to specify for all possible history. So it means that every subgame have to be specified because you need to check your strategy whether they are subgame perfect equilibrium. So that would be rather important. So so it's and I met one of the very good game theorists, and he often said he often actually apply bevel induction in daily life, right? If he often maybe work with him and always he said bevel induction, right? Look at the very end. How do you achieve this goal, right? If you want to achieve something, do bevel induction. Go back, what you want to do, and come back, right? The same as what you should do when you prepare your doctoral degree, right? Suppose you want to graduate, right? You want to write a paper with theory component, then you have to learn how to write model, right? And go back and learn the math and so on and so forth, right? It's a target oriented, right? If you want to write empirical paper, right? And in this case, then you need to collect data, you need to learn this technique here and there, then go one step back every time, and you know what to do, right? I mean, this is turned out to be how to apply Bell reduction. I mean, a solution of dynamic programming actually is very useful, right? I mean, just not just apply in theory, but in practice, you do have the idea, right? Just planning, right? Just imagine at the end of this class, you have to submit the paper, then you Bell induction, right? Look at each week what we should do. Anyway, so I hope I did cover how you solve the subgame perfect mesh equilibrium or subgame perfect equilibrium. And you will apply it into practice because I think this is most useful one. As far as you check my CV and then you see at least more than half of the paper I written is rely on subimperfect equilibrium. I mean, I do have some recent work on axiomatic, then doesn't use this subimperfect. But otherwise, when I do game theory, subimperfect equilibrium is the thing that I focus on. Of course, you can do perfect Bayesian or Bayesian equilibrium, but they are not that. Now actually it's okay, but it's more or less not so fashionable, because later you will see next class is they rely on specify the belief, and everything have to be very correctly specified. So something that I have somewhat problem, some kind of not very robust. But anyway, let's go to the game. So it's a special type dynamic game where you would repeat the same game again and again, maybe finite number of time or infinite number of time. And the question is whether the firm is able to collaborate because they compete every time, right? If they meet many times, do they able to change their behavior? Are they able to avoid coordinate failure? Are they able to achieve better outcome? So it's kind of like related to the idea of Bertrand competition or personal dilemma, right? Personal dilemma, actually later we see, you always defect, right? But in the world we observe, actually there's some collaboration goes on. Okay, so we want to say if the possibility of future interaction would change our current behavior. So that is the main thing. Is the system tomorrow will change how we do today. If there's no tomorrow, will you make a difference? So just look at this classical example, right? Because later you will see repeat game is very complicated. So many of the results in the repeat game would be focused on this simple game. Personal dilemma. Of course, that will not have this number, but personal dilemma, the game that people have derived a lot of result on. If you generalize it, then there's still some result, but personal dilemma is the most well-studied game in the game. And if you still recall this game, even without talking Nash, if players are not stupid, D is only outcome, right? Because D is dominant strategy, right? Regardless of what other people do, D is better than C, right? Because look at player one, D give him 5, right? If C give him 4, right? D give him 1, and then 0. So this bigger than this bigger than this. D is always better choice. So now the question would be, suppose they have this game again tomorrow, okay? And they discount the future by delta, right? So will be this period payoff plus delta of next period payoff. Okay? It's additive separable with discounting. And discounting factor can be 0 or 1. 0 will be just no future. 1 will be have a future. So it's considered delta discounting, or delta is probability that the future they will meet together, right? To meet again, right? So you look at this. This is a finite game, so you can do barrel reduction. Look at the last period. The last period is just DD, right? The last period, no future, right? The subgame will be same as just the playing once. So this DD. So once you know tomorrow when we met, we will go to DD. Then what we do this period must still be DD, right? Because there's nothing you can do, right? Because tomorrow you know what's going on. So what we're going to do today doesn't affect tomorrow. So today is same as tomorrow, right? Because tomorrow, you know, it's daily. So why you do different? So that means that if the game is repeated no matter many times, even n times, as long n is finite, you can always look at the last period. Last period is DD, right? And the second to last period also DD. And your barrel induction, no matter how many times you repeat, is DD. So that means that no hope, right? So we always end up in a bad outcome, right? Because CC is Pareto optimal, right? So if everything is finite, there's an end day, then you can't solve this problem. There's no collaboration, always defect. Okay. But later you will see if we don't have last period, this game can continue forever, potentially. Then you can sustain CC. Okay? So the possibility of always have tomorrow make this game infinite. And if infinite game, you can't have backward induction. So backward doesn't apply because there's no last period to backward induction. So backward induction fails or doesn't apply when you have the game that always have tomorrow, because there's no last day to go backward. Okay, backward induction have to be only applied when you have last day, right? If you don't have last day, you can't do backward induction. So in order to break the curse of defect, you have to go to infinity. Okay, so this game, suppose they play forever. Okay, can they sustain CC? The answer is yes. And we can, there are many strategies to support CC, but the literature, at least at the beginning, they focus on something very simple we call trigger strategy. Okay, is the following: they always play C if there have been C before. If there have been not CC, right, which is a complement of the first condition, they will play DD. Okay, play D if D had not been CC. So in this case, it will be CC. Why? The idea is to check if anyone won't deviate. Okay, you check. So you will check in first period. Okay, if people continue according to the plan, every period will be collaborate, right? No one deviate from that. Okay, forever, right? And that means that for over 1 minus delta, right? Because it's a geometric series. And if someone deviate, the best they can do is 5, right? That's the best thing is do the 5. And because under the Nash equilibrium, right? Under this, once you deviate, you will be deviate forever, right? So we 1 forever. So you will, this will be delta 1 minus delta, right? So you can solve this as long as you're patient. You'll prefer 4 forever instead of 5 and then 1 forever. Okay, so you prefer 4 forever instead of 5. Unless you are very impatient, of course, you would be happy for just 5. Okay, so you will check this deviation in first round and deviation on second round, right? choose another strategy that deviates second round, and so on and so forth. Actually, the same thing here. Of course, I'm a little lazy because I should have delta here. Sorry, I should. This is right. This is a period at the beginning. So this is a payoff 4, and the deviate in the second period, right? So that means that this is a Nash equilibrium, right? Because you check everything on the equilibrium path. Okay. So this is the because remember you deviate, right? The other guy keep the same. Right. So you just see whether you deviate in the first or second or third or fourth, right? Because if you deviate in the first period and you deviate second period, you can't be better than this guy, right? Because the other guy always defect, so you only can choose his own defect. Right? So that is the checking. So this is checking of Nash equilibrium. And you ask as an SPN, sorry. Then I have to check, this is more elaborate, how to check subgame perfect Nash equilibrium. So you have to check all possible history, right? Because remember what we checked in the last slide is only check the payoff at the beginning. Okay? Because you check the comparison is compared the beginning payoff to the end. Subgame perfect is to check every subgame. So that means that because we're doing a paper induction, we're doing a last period, we need to check all possible history. Okay. So to check, look at this. If all subgame has been CC, right? And in this case, the other guy also do the CC, right? So this is the same as period 1, right? Because the part doesn't really matter. So which are shown in this case. And this is something new in the SNE, right? Is if now is off equilibrium path, which in equilibrium is not reached, right? In the equilibrium, there's no CC, right? Always CC. So the check is when it's not CC, which is not equilibrium, the check is DD is a Nash equilibrium, right? Because if it's not CC, you're supposed to choose D. The other guy also choose D. Okay. And under other guy D, are you going to choose other thing? The other thing is not, because if other guy choose D, you also choose D as well. Right? There's no way you can gain from that. So that is the new thing you need to check. Okay. Different from before. You can argue that for every possible history, which might or might not be equilibrium, so that your strategy remain right. Okay. And you probably would worry about one thing which I didn't show. I should have shown here is it is so complicated, right? There are many strategies. How can we check? Do I write down here? Oh, I have here. Later we'll see. Okay. We have what we call the one-shot deviation principle, which means that you only need to check any possible history. You only deviate at the current period. Okay. You don't need to check very complicated deviation strategy, which I will elaborate later. Okay. But for this, this is easy. So at least we show you one thing. If personal dilemma forever is able to sustain cooperation. Okay. And that implication, you may wonder why, I'm not sure whether you get married, but if you get married, actually sign a contract. And that contract has no time limit, right? And you get married, and you get married supposed forever, right? Of course, you can divorce, but there's no end of the period. And of course, there's some place in the world actually the marriage contract has a period, right? But you will see why marriage has no end period, right? Because if you expect marriage has last period, the last period, what will you do, right? And probably try to grab as much as extract as much money from the family as possible, right? Because tomorrow you go to divorce, right? So probably you hide the money, right? You next period you separate, right? So what you do? Hide as much money as possible, right? Right? You don't want it to happen, right? Because last period. Okay. So, and that's not unusual. And probably you will see Hong Kong is the one of the most expensive place in the world in terms of housing. You will ask why. And that's because in the 80s, Chinese government worry about the British government would sell everything in Hong Kong if they know they're going to turn over Hong Kong in 1997, right? You will try to use all the money up and sell all the land, so nothing left, right? So that's why at the time they limit to 1984, they not limit. Each year they only sell 50 hectares of land. Of course, now they no longer limit, but anyway, that's another story. But that's why from 80s to 90s, number of land they can sell is limited. And they are not allowed to use a lot of welfare policy because they worry about they bankrupt the whole government. Okay, which is in the hindsight is not something. Worry is not wrong because look at Macau. Actually, when they before they turn over to the China in 1999, they actually spent all the money in the government because there's no such a contract. So they get out, they just spend all the money before they turn it back to China. So anyway, but that is because you know the last period, right? So that's why they do it. And same the US. When I look at the president of the US, they have the right to give clemency, right? So which means that if you have a crime, the government, the president can get you out of the jail, right? Because that is the right of the president of the US. And you notice that the president don't use this right in the first 3 years. At the last few days, they will sign a lot of that. Okay, to those who actually do a lot of contribution to him, right? So basically, at the end of the few days, they just do whatever they want because they're out of power anyway. So just do whatever thing at the end. Okay. So the deadline is very important. So when the end day, then you know it's going to end, and that's why people will do crazy things. And that's why when company fire somebody, right? So you will immediately terminate the access of the guy. Okay, even he may stay there for a few days, right? Basically, he will cut off all the assets. Otherwise, he may copy things from the computer, steal the company's secret, so on and so forth, right? So once someone is fired, even he may stay there for 1 week or so, he lose access for many things, right? Because worry about last period, he do something crazy. Or you can look at why a lot of shop are charging a lot of very high prices for tourists, right? Instead of local people. Local people, they are not cheating. But tourists, they try to charge very high price. Right? Look at many places in China, right? You go to a very famous tourist spot, right? When you go there, they try to say, oh, no, this is not the price, not 100, it's 200. Why? Because they know you're not coming back anyway, right? So there's no future interaction. They will charge you as much as they want, right? You know there's no more future interaction. Why don't just do it once and for all, right? Grab all the money and go, okay? So here comes another example to show you that even if you have a game that has, if you have more than, if there's some outcome that, let me see. If your game that has some outcome that Pareto dominates the Nash equilibrium, okay? There's a B here, Pareto dominates that. It's possible to support non-Nash equilibrium. Okay. So let's see. So the put it this way, I put this way. If you have more than one equilibrium, then you have when we play the game, you can support something non-Nash equilibrium in the first round. Let me say it again. So if the game has more than one pure surgeon Nash equilibrium, okay, if you repeat the game, you can support something that is not Nash equilibrium in the first round. How can we do that? It's like stick and carrot, okay? Punishment and reward. How are we going to do that? Remember, the trigger strategy is you always collaborate, and if things doesn't work out, you punish. Okay? Actually, you can do the same if you have something similar. Okay, you have good equilibrium and bad equilibrium. B.B. is a good equilibrium. D.D. is a bad equilibrium, right? B.B. you can check is a Nash equilibrium. So you will see by construction or by induction, you can have D.D. as a subcamp Nash equilibrium, right? Both period D.D, right? Or both period B.B, or mix and match, right? B.B, D.D, D.D, B.B, 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 D.D, D.D, right? 2 by 2, right? Both period, maybe just write down. Both period B.B, and B.B is a Nash equilibrium, is a subcamp Nash equilibrium, or B.B and D.D, okay? Or D.D and D.D, okay? And also B.B, B.B, B.D, D.D, and B.B, right? Okay, that's 2 by 2, right? So these 4 are subcamp perfect Nash equilibrium. Okay, so they are all Nash equilibrium in their own, so that's not surprising at all. What's surprising is you can support a Pareto efficient outcome, CC, which is not Nash equilibrium in if you just play once. You can't support CC at the last round because it's not a Nash equilibrium, but it can be a Nash equilibrium first round. How do we do that? Suppose payoff is just adding up, no discounting. Okay, just add up 2 period. So we will say the SPE will be CC. Okay. If CC, then will be BB. Okay. If not, will be DD. So if we are nice, we collaborate on C, we go to good equilibrium. If not, we go to bad equilibrium. Okay. So by barrel induction, we don't need to check the last period, right? Because they're natural equilibrium. We only need to check the first period. So if you follow the equilibrium, you get 4 plus 3, which is 7. If you deviate, you become a naughty guy, you just deviate to 5, right? But once you deviate to 5, the next period we end up in the bad outcome is 1. So it's 5 plus 1 is 6. So 7 is better than 6, right? So you don't deviate because you know if you are being knocked in the first round, everyone will go to 1. Okay. So knowing that if you don't do well, right, then then you will get to here, right? So that's you. How can you sustain a good outcome? Okay, is by having a nice outcome and bad natural equilibrium. By threatening if you are being not nice in the first round, we will get into a bad outcome. Otherwise, it will be peaceful. Okay. So is that clear? So that is very important, right? Here you can see the good and the bad outcome are Nash equilibrium. You can support something non-Nash. So here means that it's very important, right, to see good outcome non-Nash can be supported. So that means that you look for equilibrium when things repeated. You have to check out whether things like this can be done. Okay, is that okay? So of course, there's a lot of things can be done on this final game, but our time is constrained, so we focus on only on infinitely with the game. So we'll introduce some notation, and then we'll break. So repeat game is very simple. It's just N, A, and U, and this is simply normal form game, right? The only difference is we have another thing called T, which is an integer, okay, or infinite. So basically T is an element of R plus, right? Of course, R plus extended R, should be M plus, maybe better. M plus plus and infinity if you want to be something very serious, okay, this like this. And so this is the game. So we play this game many times, okay? And here, as we see, same as before, right? Because this is a special case of the game we have. So history will be action for all the game. So here, with the game literature, we start from period 0. Okay. So that's why 0 up to t minus 1. And sometimes we refer strategy is behavioral strategy, which means that for every history, you tell me what to do, right? So because strategy should be, you tell them for all history what to do, right? But here it specifies a function in this way, okay? And strategy play I will be some of this, right? Because this will be for all time, okay? It's a strategy at time t and strategy for all time, okay? So this is behavioral, this is normal strategy, okay? and strategy profile like this. So another terminology will be path generated from strategy, which means that what action will be taken under this strategy. Okay, because later you will see what do you mean by that. Okay, and the payoff will be because this outcome, right? So this all the outcomes based on the strategy, okay, and just discount every period. Okay, so this is some terminology here, and nothing surprising. Next equilibrium will be a profile that you choose this strategy better than you choose all other strategy, given other guys are keeping the same. Nothing new there. Just check. And subgame perfect will be checking all possible history. So the only difference is all possible history, whether the history is reached or not. Okay, that's for all. Okay, so of course the formality is very difficult, but the idea is very simple. It's just to check all possible history. Okay, and before the break, I want to mention this very important point. Actually borrowing from dynamic programming as well. In all the game that I think you analyze, unless we're special game, you only need to check what we call one period deviation. So you only check all possible history. You only check whether in this period, you only want to deviate or not. You don't need to think about a complex deviation scheme. Okay. So basically you check, say, pressure dynamic. At this period, I want to deviate or follow. Just deviate only about this period. And after this period, I should follow the old continuous strategy. Okay. I don't need to devise, I deviate this period, next period I follow, the next period I deviate, and I follow, and I deviate, not follow. I don't have a complex scheme. I just need to check. I only deviate only this period. And after that, I follow my current strategy. Okay. I don't need to check many complicated things. That means that I reduce the number of checking. Right? Because imagine, right? You have to check every single strategy, deviate, right? You check if other strategy better than this, right? Remember, right? Here you check all, right? So one short interval means you only need to check whether only the strategy compare, they are only different in the current period. The future period, they are the same. Okay? That is the content of this one short interval. You only need to focus on comparing the strategy that is different today. Tomorrow, all the same. That is sufficient. And you ask what assumption needed to drive this. If you check the textbook by Fildenberg and Tiro, they will tell you the condition we call continuity, payoff continuity at infinity, which simply means that it doesn't really matter at the end of the day. So basically, if you are discounting, doesn't really matter. And this would apply to the game you analyze. So basically, you don't have to worry about this. This would also apply, unless you're going to a very technical game that doesn't belong to anyone have analyzed before. So you only need to check something very simple. Otherwise, you check very complicated strategy. Okay. We will show you after the break, so don't worry about that. So let's resume 11:45, and we will see how to apply this in practice. Okay. Oh, I think I didn't go to this, but if you, in case you haven't filled in, please fill in and then we can go over that. Yeah, we'll break until 11:35. Into space. Sorry about that. Can't be away. Speak of that. But I now know that this is some of the. Surprisingly, because my boss always told me when I was too fancy. Because I always like as sweet as possible, maximum sweet. Like I said, local association. Or you can, I'm not too sweet. What that?